Welcome to DriverDTrains. Thanks for stopping by. I'm your host, DriverD. Our conductor and brakeman, Scratchy-C, is up to something. In December 2024, DCC-EX announced the release of the EX-CSB1 Express, an all-in-one plug-and-play command station and booster. In my last video, we looked at how to customize our DCC-EX command station's display by editing the EX-CommandStation code in the Arduino IDE. In this video, part 5 in the series, we'll look at how to add a second display to our DCC-EX command station. All of the examples we look at today will work with any DCC-EX command station, not just the EX-CSB1, and we can configure our new display using either the Arduino IDE or the EX installer. Be sure to check this video's description for links to my other videos, as well as the various websites and products I mention here. Also, if you are enjoying the videos, please leave a comment and hit the like button. And if you haven't already, be sure to subscribe to the channel. There's lots to see in today's video, so let's get this train rolling. Add a second display to our DCC-EX command station. Now that we've learned how to use the Arduino IDE to customize our DCC-EX command station's display, let's look at how to add a second display to our DCC-EX command station. For this discussion, I will assume that you already have one display attached to your command station, either because you added it yourself or because you purchased an EX-CSB1 with a display included. At several points during this video, I will refer you to my prior video, number 4E, adding an LCD display to DCC-EX, as well as the previous videos in this series if you need additional information on how to connect and customize your display. Here are all the messages on today's train board. First, we'll start with the hardware by looking at the different types of displays we can use, how we can set the hardware addresses for those displays, and connect them to our DCC-EX command station. Then we'll update the EX-CommandStation software to confirm our new display's address, configure the display, and then look at some ways we can put our new display to use. We've got our orders, so notch up the throttle, release the brakes, and we'll move on out. Add a second display to our DCC-EX command station. Preparing the hardware. Part 1. Display options, LCD and OLED. Let's start by looking at some of the different types of displays that we can connect to our DCC-EX command station. For this discussion, I will assume that your command station already has one display. If not, be sure to check out my video, number 4E, adding an LCD display to DCC-EX. The DCC-EX EX-CommandStation software supports two broad categories of display screens. These are LCD character-based displays and small OLED displays that can be used as character-based displays with a suitable graphics library. These types of displays typically support from 2 to 8 lines of text. LCD and OLED displays come in multiple sizes, both in terms of their physical dimensions as well as the number of characters or lines of text that they can display. The LCD screens that DCC-EX supports come in 2 sizes. The smaller screens can display 2 lines of text at a time, with up to 16 characters on each line. The larger LCD display screens can display 4 lines of text at once, with up to 20 characters on each line. OLED displays come in a wider variety of shapes and sizes. The typical OLED displays that DCC-EX supports range in size from just under 1 inch to about 1.3 inches across. These displays have a nominal resolution of 128 by 64 pixels, although some displays use a driver chip called an SH1106 that has an actual resolution of 132 by 64 pixels. These are the displays that DCC-EX is currently using with the EX-CSB1. There are also 2.4-inch versions of the OLED displays that also have a nominal resolution of 128 by 64 pixels, although again, some have an actual resolution of 132 by 64. These are much larger in physical size and easier to read from a distance than a 1 or 1.3-inch display. Note, however, that most 2.4-inch displays use an interface called SPI that is not compatible with DCC-EX. We need to make sure that we find a version that is pre-configured for the I2C interface, as we'll discuss in a moment. Some displays claim to work on both SPI and I2C. They do not, without considerable modification. I'll include a link to the correct version of the 2.4-inch display, as well as some of the smaller displays in this video's description. Note that OLED displays require us to solder header pins to the board before we can use them. The displays come with straight pins, but we can also purchase 90-degree angled pins if we prefer those. All of these OLED displays support up to 8 lines of text, with 20 characters on each line. The difference is that the text characters appear larger on the larger screens, although not as sharp up close. There are also half-height versions of the 1-inch screens that have a 128 by 32 pixel resolution and support up to 4 lines of text. Both LCD and OLED displays are also available with the display text in different colors. Common colors include white, blue, green, yellow, and red. Most LCDs have white text, but some are also available with black text and with different color backlights. I'll include links to some of the displays that I have tried in this video's description. Part 2. The I2C Interface and I2C Addresses. All of the displays that DCC-EX supports need to have an I2C interface. Also called I2C or IIC, the Integrated Circuit Interface is a popular 2-wire serial communications protocol for connecting peripherals to processors and microcontrollers. As its name suggests, the I2C interface uses 2 wires for serial communications, a data line abbreviated SDA, and a clock line called SCL. However, I2C devices also need to have power and share a common ground, so I2C connections typically use 4 wires: power or voltage called VCC, ground or GND, the data line SDA, and the clock line SCL. You can learn more about the I2C interface in my video number 4E, Adding an LCD Display to DCC-EX. All I2C interfaces used with any specific controller, such as our DCC-EX CommandStation, are connected to that device in parallel on the same communications bus, using the same data and clock lines. That means we can piggyback I2C devices together, or daisy-chain one I2C device after another. However, in order for our controller to be able to communicate with any specific I2C device, each device must have its own unique I2C address. We'll discuss how to figure out what a device's I2C address is and change the address later in this video. There is a narrow exception to the unique address rule for displays. Because displays only receive information and don't communicate back to the controller, multiple displays of the same type with the same screen resolution can coexist on the same I2C bus. They'll just show the same message on each display. For our DCC-EX CommandStation, this can come in handy if we want to show our CommandStation's status and Wi-Fi information or any other information on multiple displays spread around our layout. However, if we want to show different information on each display, we need to change the I2C address on at least one of our displays. This involves soldering across some jumper pads on the display. The exact way that we change the I2C address for each display depends on the display. LCD displays are generally easier to work with in this regard. Many LCD displays have an I2C backpack that has a series of 3 solder pads, typically labeled A0, A1, and A2, that allow us to change the I2C address to one of 7 additional addresses. For example, the default I2C address for many 20-character, 4-line LCD displays is hexadecimal address 27, which is written as 0x27, and this is the I2C address listed in the EX-CommandStation config.example.h sketch. However, if we solder across the A0 pad on the backpack, the I2C address will decrease by 1 to 0x26. If we then soldered across the A1 pad, the address would decrease by 2 more to 0x24. We can use combinations of the 3 solder pads to change the LCD's default I2C address from 0x27 to anything between 0x20 and 0x26. Unfortunately, OLED displays do not offer as many address options. Most OLED displays offer 2 address choices that can be selected by moving a 0-ohm resistor from one solder pad to another. The exact location and configuration of the resistor varies from manufacturer to manufacturer, and not all displays include one. I've had trouble working with the tiny resistors, which resulted in poor connections, but we can do away with the resistor and just solder across the pads with a small bit of wire if necessary. The default I2C address for many OLED displays is 0x3C, with the optional address being 0x3D. These are equivalent to 60 and 61 in decimal form. However, most of these OLED screens will have 0x78 and 0x7A printed on the boards. These are equivalent to 120 and 122 in decimal form. The reason for the discrepancy is that the I2C hardware designers bit shift the 7-bit address in an 8-bit byte, which effectively multiplies the address by 2, but the coders of the Arduino software libraries that we use to communicate with I2C devices use the unshifted address. So we will need to use the unshifted 0x3C or 0x3D address when we configure our OLED displays later in this video. Because OLED displays typically offer only 2 I2C address options, it means that we can only add one additional display to our DCC-EX command station's I2C bus, unless we want to add a display that mirrors another one. In my next video, we will look at how to get around this limitation by adding an additional piece of hardware to our communications bus known as an I2C multiplexer. As I mentioned previously, for LCD displays, we can choose up to 7 additional addresses to use. However, we can't easily use LCD displays with the EX-CSB1 because most LCDs require 5 volts on the I2C bus to work, and the EX-CSB1 is only rated for 3.3 volts for I2C. Again, there are ways around this limitation that we'll explore in a future video. But for now, for the EX-CSB1, we'll want to stick with OLED displays, which typically work on both 3.3 and 5 volts. We'll consider some more of the particulars of the I2C bus next. Part 3. Connecting our display to the I2C bus. To connect our second display to our DCC-EX command station, we connect it to the command station's I2C bus. There are several ways to do this, depending on which command station we are using. In my video number 4E, Adding an LCD Display to DCC-EX, we looked at how to connect our display to the I2C pins on the motor shield. There are actually 2 sets of I2C pins on the motor shield, so we can easily add a second display directly to these pins. There are also I2C pins in the GPIO headers of the Arduino itself. On the EX-CSB1, there are also a number of different locations where we can connect to the I2C bus. There are 2 sets of I2C pins next to the I2C header for the built-in display, although the display partially covers them. There are also I2C pins in the GPIO headers on the board that match those on the Arduino. And finally, the EX-CSB1 also features a Stemma Quick I2C connector, which is based on one of the smallest members of the JST, Japanese Solderless Terminal, family of connectors. We can purchase special cables with the Stemma Quick plug on them to connect our displays. One important thing to note is that, except in the case of the Stemma Quick connector, there is no standard for the order or arrangement of the I2C pins. In other words, the pins will be in a different order on different displays and different command stations and motor shields. For example, on some displays, the order might be ground, VCC, SDA data, and SCL clock, while on other displays it might be ground, VCC, clock, and data. The header for the OLED display on the EX-CSB1 has this latter arrangement. However, the two rows of I2C pins just next to the OLED header are ordered SCL clock, ground, SDA data, and VCC, so go figure. The order of the pins in the stemma quick connectors is standardized, as are the colors of the wires in the cables, with black being the ground, red the VCC, blue the SDA data, and yellow being the SCL clock line, in that order. I always remember that yellow is the SCL clock line on the stemma quick connector because yellow has two L's in it, so it goes on the SCL pin of the display. We need to make sure that we pay very close attention to which pins are which when we connect our I2C cables, because the odds are that the pins will be in a different order on each end of the cable. It is very common to mix up the clock and data lines. Although this won't ruin the display, it also won't work that way. Another factor that we need to consider and pay attention to is the operating voltage of the command station and what kind of displays are compatible with that voltage. Traditional Arduino microcontrollers and compatible clones run on 5 volts, so we can use either LCD or OLED displays with DCC-EX command stations based on those controllers. ESP32-based command stations, however, such as the EX-CSB1, run only on 3.3 volts, so we can't normally use 5-volt LCDs with them. There are ways to get around this limitation with additional hardware to level shift the voltage, but that is beyond the scope of this video. So for the EX-CSB1, or most other ESP32-based command stations, we want to stick with OLED displays, which work on both 3.3 and 5 volts. Something else to consider when attaching our displays to the I2C bus is what kind of cables to use. While we can use breadboard jumper wires, such as those I described in my video series on assembling a DCC-EX command station, or the small stemma connectors to connect our displays to the command station, we don't have to use those and might prefer something more robust that we can use over a longer distance. One convenient option is to use computer Ethernet cables. We can easily connect an inexpensive RJ45 Ethernet jack breakout board with pin headers on it to our command station, and then run an Ethernet cable of whatever length we like to another RJ45 jack that we can attach to our display. And since the RJ45 actually has 8 wires in it, we can conceivably use it for more than just the I2C bus, or more than just one display. Finally, while there aren't any I2C splitter cables that I'm aware of, there are inexpensive I2C breakout boards that we can use to connect up to 7 additional I2C devices to our I2C bus. And we can use any or all of these connection strategies together. So for example, we could use a stemma quick connector or other jumper wires to connect an RJ45 jack to our I2C bus, then run an Ethernet cable to another RJ45 jack, attach that to an I2C breakout board, and then attach additional displays to that. And by using some displays with the same I2C address, we can have important or useful information from our command station available at multiple locations around the layout. We have now looked at the basic hardware considerations for adding a second display to our DCC-EX command station, including the different types of displays available, how to change their I2C addresses, and how to connect them to our command stations. Now let's look at how we can configure the DCC-EX EX command station software to use our additional displays. Update the EX command station software. Part 4. Confirm our display's I2C address with I2C scanner. Now that we've connected our new display to our command station, let's configure the DCC-EX EX command station software to recognize it and look at how we can use it. The first thing that we will want to do is confirm our new display's I2C address and that it is connected and visible to the command station. We can use DCC-EX for this. First, however, I will mention that there are also sketches that are designed specifically for identifying I2C devices connected to our I2C bus, and both the Arduino and ESP32 code libraries include examples that we can use in the Arduino IDE. We can find these in the File, Examples, Wire menu. There are numerous other variations of the sketch with different names available from other sources, but they all do the same thing and any of them would work. We just need to make sure that the serial communication speed specified in the code matches the baud rate setting for the serial monitor in the IDE. However, we don't need to use any of those sketches because the EX-CommandStation software already includes and runs the necessary code at startup. The specialized, task-specific sketches I mentioned previously can be helpful if we are troubleshooting several I2C devices at once or making a number of modifications to our hardware setup. But for most situations, we can simply use DCC-EX. As I mentioned, DCC-EX will run the I2C scanner code at startup and send the results to the CommandStation microcontroller's serial output. We can view this output in one of many different places, including the IDE serial monitor, the EX installer device monitor, the EX web throttle debug console, and the JMRI DCC++ traffic monitor. Unfortunately, in many cases, the DCC-EX I2C scanner code runs before we are able to establish a serial connection to our command station, so we may not see the EX-CommandStation I2C scanner's results. However, we can easily reboot the command station by entering open angle brackets, capital D, reset, close angle brackets on the command line in the Arduino IDE or EX installer, or simply capital D reset without the angle brackets in JMRI or the EX web throttle app, and then pressing return or enter. Our command station will restart and we'll see the I2C scanner results in the output window, including the I2C address of our original display, as well as the I2C address for the new display we just added. Part 5. Configure our new display in EX-CommandStation. HAL Setup. Now let's configure the EX-CommandStation software to use our new display. To do this, we are going to add a new sketch to the CommandStation EX code called myhal.cpp. HAL stands for Hardware Abstraction Layer, and it provides an interface between the software and the hardware so that our software, EX-CommandStation in this case, will work as expected regardless of what hardware we are using. We can create this new myhal.cpp sketch in the Arduino IDE, or by creating a new plain text file in the myEX-installer folder where we stored our EX-installer configuration files in video number 8B, Configure DCC-EX, EX-CSB1 with EX-installer. While we could add the new display configuration in our myautomation.h sketch, we are going to use the myhal.cpp sketch for other things in this video, so we'll configure the new display here as well. Note that, for the purposes of this video, I will be showing the myhal.cpp sketch in the Arduino IDE, but we could just as easily write all the code in the EX-installer app and save it in our myEX-installer folder. We'll create the new sketch or text file, then enter the following code. Hashtag include, quotes, io_haldisplay.h, end quotes. This will allow us to add new displays to our hardware abstraction layer. Remember, all the capital and lowercase letters and punctuation need to appear exactly as shown. I will include all the code from today's video in a community post on my channel. Next, we'll create and configure our new display in the sketch. We'll do this by adding a HAL setup function as follows. Void HAL setup parentheses open curly brackets. Then we'll create and configure the display. We can do this for both LCD and OLED displays. For each display, we'll need to assign it a number. The original default display that we defined in our config.h sketch is display number 0. The additional displays we define in the myhal.cpp sketch start at number 1. For example, for a 20-character, 4-line LCD display with an I2C address of 0x26 that we want to be screen number 1, we would write the following. HAL display, open angle brackets, liquid crystal, close angle brackets, colon, create, open parentheses, 1, 0x26, 20, 64, close parenthesis, semicolon. For an OLED display as screen number 2 with an I2C address of 0x3D and a 132 by 64 resolution, we would write HAL display, open angle brackets, OLED, close angle brackets, colon, create, open parentheses, 2, 0x3D, 132, 64, close parenthesis, semicolon. Note that we didn't have to choose screens 1 and 2 for these examples. In theory, we could have chosen any numbers from 1 to 254 for either display, although for some reason EX-Rail automations do not seem to work with anything above 242. We can also create software definitions for the displays here in the hardware abstraction layer, even if those displays don't exist. The code doesn't care. Once we are done creating our display, we end the HAL setup function with a closed curly bracket. Part 6. Using our new display in EX-CommandStation. The screen command. Now that we have created our new display in the EX-CommandStation code, we want to use it. To do this, we use the DCC-EX screen command. The screen command works just like the LCD command we used in the last video, except that we indicate which screen number we want to display our text on, along with which line number. There are two ways we can use the screen command: in our EX-Rail automations and in the EX-CommandStation code itself. For example, in our myautomation.h sketch, either in the Arduino IDE or in EX Installer, we can add the following line of script to the auto start sequence for the LCD screen we defined earlier, or this line for the OLED screen. Then we can upload our sketch to the command station, and when it reboots, we should see the Hello World message on our new display. We can now use the screen command in any of our EX-Rail scripts to show messages on our new display. We can also use the screen command in the EX-CommandStation code in the Arduino IDE, the way that we used the LCD command in the last video. We just need to add which screen number we want to display our text on. And remember, just like with the LCD command, we need to use the ftext function macro for the text we want to display. So for example, suppose that instead of displaying our command station's Wi-Fi information on lines 4 through 7 of the main display screen, we wanted to display that information on lines 0 to 3 of our new display. To do that, we would change the LCD commands in the Wi-Fi interface.cpp and the Wi-Fi ESP32.cpp sketches to be screen commands. Add the screen number that we configured in our myhal.cpp sketch for our new display to the command just before the line number, and then change the line numbers 4 to 7 to be 0 to 3 accordingly. Now, the first 4 lines of information that EX-CommandStation displays, including the version number, power status, and free memory, will be on our original display, while the Wi-Fi information will be on our new second display. We can also use screen commands in our EX-Rail automations and the EX-CommandStation code together. By adding screen commands in our myautomation.h sketch or other automations, and using screen commands in the EX-CommandStation code, we can configure our new displays just the way we like. One thing to note is that any displays we might add that have fewer than 8 lines will not scroll from page to page to show all the lines of text if there are more than the display will show at once. Also, the individual lines will not move up the display to fill in any blank lines the way they do on the default display. Display information about our locomotives. Now let's look at an example of how we can use our new display to show information about our locomotives. To do this, we will add some code to the myhal.cpp sketch to create a new function that will show the information we want to display about our locomotives, and then add a user add-in to the HAL setup function where we created our new display. Here's what that code looks like. The code is based on a sample provided by DCC-EX in the myhal.cpp_example.txt file. The code must appear above and not inside the HAL setup function. Again, I will include all the code in a post on my channel community page. This code creates the Update Loco Screen function, which uses the same locomotive speed table information that we used in the example from the last video to display information about our locomotive on our main screen. In order to include information from the DCC locomotive speed table in the Update Loco Screen function, we need to include the DCC.h sketch here in myhal.cpp, which we'll do with a #include statement. The Update Loco Screen function will display information for up to 7 locomotives on whichever screen we select, in this case the OLED that we created as Screen 2. You may notice that this version of the code uses binary math to convert the speed from 0 to 255 to 0 to 127 forward or reverse, which is more efficient and eliminates the need for the if statements from my last video, although a bit harder to decipher. Now, to actually call or run or execute this Update Loco Screen function, we create a user add-in in the HAL setup function. So in the HAL setup function, just below where we created our new display, we'll add the following command: user add-in : create, open parenthesis, update loco screen, 1000, close parenthesis, semicolon. What this does is tell the EX-CommandStation software to call our Update Loco Screen function to display information about our locomotives on our new screen every 1000 milliseconds, which is to say, once per second. Now, if we upload our code to the command station, when it reboots, we will see the title Active Locos on our new display, and when we select a locomotive from the throttle, we will see its speed and direction shown on the screen. We can select more locomotives and their information will be added to the list, with up to 7 in all. However, if we run this code on a 4-line LCD screen, we will see that only information about the first 3 locomotives is shown, and the screen doesn't scroll to display information about the other 4. Instead, information about the last locomotive overwrites the bottom line of the display. That is because the screen command executes a different set of code than the LCD command, and they are not exactly the same. As a result, as I mentioned before, our second display, or any others that we might add, will not scroll to show additional lines when we use the screen command. However, we can implement our own scrolling code to show not just 7 locomotives, but as many as we are able to run in DCC-EX, and the display will scroll through the entire list, then cycle back to the beginning. Here is that updated version of the code and how it looks in action. Again, I'll also include this code in the post on my community page. A fun startup animation. Finally, how about we have some fun by displaying a startup animation whenever the command station boots? We could also create EX rail automations to display an animation like this when a train reaches the station, when a signal clears, or just randomly from time to time. Again, you can find the code for this animation in a community post on my channel. What's next? Add a display to DCC-EX using an I2C multiplexer. In my next video, we'll look at how to add even more displays to our DCC-EX command station using I2C multiplexers and explore some additional ways that we can use those displays to show information about our trains. Be sure to subscribe to the channel so you don't miss any upcoming videos, and check this video's description for links to my other videos, including my video series on assembling a DCC-EX command station and my series on using JMRI's Decoder Pro app to control our trains. We've completed our deliveries for today, but there are already more cars waiting in the yard, so we'll rest while we can and be back at it again soon enough. Until then, Thanks for watching. Scratchy, what are you doing on GitHub? Artificial General Intelligence? All aboard!